All right, so let me announce the first speaker is Jon Lee from Michigan, and he's giving a talk in his Gaining a Losing Perspective series.
Thanks, Siri. So yeah, first I want to do some thanks. First I want to thank Dan Beanstock, who 18 years ago had the vision to see that MIP kind of broadly defined should be an enduring topic, and kind of the audacity to believe that mainly young people organizing it without any real governance would be the success that it clearly is. So thanks a lot to Dan. I also certainly want to thank the organizers, Timo, Yuri, Robert, Carla, and Yuan. So yeah, I originally intended to give this talk a year ago. Since then, I thought maybe I would gain some perspective, but really in the last year, I've mainly been losing it. So this is joint work with Daphne Skipper, Emily Speakman, and Luza Shu. Luza is a student of mine. This work involves the so-called prospective reformulation. This is something that's useful in the presence of indicator variables, where an indicator variable, when it's off, means that some vector, or often a scalar of decision variables, is forced to be 0. But when the indicator variable is on, then the decision variables can be in some polyhedron. Often we're just in one dimension and it's an interval. So there are lots of applications, even in the one-dimensional case, where x is either 0 or it's in some operating range L to U, and there's a variable kind of cost function f of x, and having the indicator variable, which we'll call z later, allows you to have a fixed cost for operating. And if you're operating, then there's a variable cost, this f of x, for being in that interval LU. So there's lots of examples. Example that we analyze in a lot of detail is just power functions, convex power functions. So the exponent is a positive, a real number greater than 1. But there are plenty of other examples like that. Or you can even look at sort of combinations of these things, like look at a Maclaurin series with positive coefficients, that kind of thing. So lots of examples. I'll tell you exactly what I mean by the prospective reformulation in a moment, but what you should realize is that when you make these kind of perspective transformations of arbitrary convex functions, you're led into conic programming, and you have to have a barrier for the appropriate cone. If we're looking at quadratic functions, it's just an ordinary SOCP setting, and you can ignore that at your own risk. And what I mean by that is you can do the perspective transformation and feed your problem to an ordinary solver that's not cone aware. And that can lead to all sorts of trouble, because you don't have constraint qualifications normally holding, even for this very simple perspective formulation. And so if you want to be safe, and I think we tend to want to be safe if we're embedding this in like a branch and bound, where we're going to be discarding subproblems, we really want to solve them fairly exactly. Then if you want, and Dan sort of talked about this quite a bit in his talk yesterday, if you really want to be safe, you want to be really sure you've solved the problem, then you really should be solving these relaxations accurately and carefully, and that really puts you in the realm of conic programming. If you want to include general constraints, nonlinear constraints, at the same time as conic constraints, you're a bit out of luck with solvers, most solvers these days. So solvers that are cone friendly like Mosaic aren't so friendly to arbitrary nonlinear constraints, and things like IPOpt aren't friendly to conic constraints, unless you want to bring your own barrier function, which is a pain for most users. So what are we going to do? We're going to look at the different options for making this kind of perspective reformulation or not, and seeing what we lose. And the way we're going to measure the quality of a relaxation, there's flaws to it, but it's something I quite like, is looking at the volumes of the relaxations. So I'll get into that, what I mean by that in a little bit. Let's make some definitions to see exactly what formulations I'm talking about. So these formulations are in 3 dimensions. There's variables x, y, and z. And first we think about the disjunction, that we either have x, y, and z all equal 0. Z is just this indicator variable that says either that X and Y. I haven't said what Y is yet, but here's X should be 0, or X should be in some operating range. And the idea is that Y is modeling f of X. And in many situations, you're minimizing Y and actually pushing it down to the value f of X. Other times you can't quite control that, and it's just an upper bound on f of X. And well, since you're between L and U, and we assume some convexity, you can make this kind of lid on Y in the space of X and Z. It's just really involves the variable X, and it just says, well, how big can Y be if Y is supposed to be f of X? Well, I just look at Y at the two endpoints and put a lid on this set. And that's what this simple upper bound is on involving X, is linear upper bound on Y. So you can, three-dimensional set, why not just take the convex hull? And that's the perspective relaxation. So roughly speaking, what you do is you perspectivize f of X. What that means is divide by a new variable Z, which is positive, and inside of the f, and then you multiply by Z on the outside. I'll draw a picture in a second, but that's what perspectivizing is. At the same time, you can perspectivize the lid, this linear function, and you get a different linear function now involving the variable Z. But it's still a linear function, so we still have a nice convex set. It's convex because the perspective of a convex function is well known to be a convex function. The only other little thing to realize is that you do this kind of shrinking and telescoping of the interval L to U, and you'll see in the picture what that does in a second. So that's the perspective relaxation. It has this annoying business that I don't really write it down fully because I have to take the convex closure, and that's because I have Z positive here and I'm dividing by Z. I can't let Z really go to 0 and give it to a solver, so I've got to deal with it implicitly, and that's why we go into conic programming in a sense. So that's one of the reasons. A simpler relaxation, which is what your master's student would do, is what we call the naive relaxation. Now this needs more assumptions. We have to assume not only is f defined on L to U, but it's defined on all of 0 up to the upper bound U. And the reason we have to do that is because we don't do this perspective transformation anymore. We just leave the function f of X there. And so since we don't scale X down by the Z factor, and it's still getting scaled down here, we've got to do something, and the way we deal with that is by assuming that f is defined on the whole interval from 0 to U. I didn't really say this, but maybe it was obvious to all you MIPers that the reason for this is that if Z is 0, that forces X to be 0, and if Z is 1, it allows X to be between L and U. I should have said that sooner. So these are the kind of sets we look at, and in some earlier work, we compared these two things, allowing the F and L and U to be different, and try to understand for which F or what L and U these things are close to each other. Because if they're close, we can get away with this relaxation, which is much lighter, easier for solvers to handle. Just a little picture, if you like pictures. This is what the perspective transformation is doing. So I have the graph of the function f here. This is the lid I was talking about. And when I perspectivize it, I just sit here at the origin. I'm living here in the plane z equals 0, this kind of flatland. And then I look up to the graph of the function in the z equal 1 plane. And if I just take the convex hull now between the origin now and this little moon, so I just take this kind of perspective, look up at it, that set is the perspective relaxation. If you're interested in what the naive relaxations look like, and a whole family of relaxations between the perspective and the naive relaxation, you can look in this paper here, which is soon to appear in JOGO. Yeah, what's a little history for me? The sets we're looking at are three-dimensional sets that we want to compute the volume of. I've been doing that since the 1970s when I took calculus. And then it was usually called Analytic Geometry and Calculus. That's my actual calculus book that I studied from. And we computed all sorts of volumes of three-dimensional sets. But I was really an amateur then. And then I started doing it professionally in 1994 with my friend Walter Morris, trying to see what the volumes are of sets that can be relevant to combinatorial optimization. So as I said, we compared the perspective and naive relaxation before. That's this paper here. And what I'm talking about today, if I ever get to it, is this. So it's the same basic idea, but now I want to understand when it might be useful to take that convex function and first piecewise linearize it, which is a very common trick to go from the nonlinear world to a linear world modulo some discrete variables to manage the piecewise linearization. And so that's what we'll talk about here. And you'll see things get much more complicated, but still somewhat tractable. Later I'll mention something about that. So piecewise linearization, this is all trivial. I just want to set the notation. So I have the interval L to U, and I think about linearization points, Xc0 through Xn. Xc0 and Xn are just the endpoints L and U, and then I have these other linearization points. So at these linearization points, there are tangent lines. So I'll call them T sub I. That's the tangent line at the contact point, Xi, f of Xi. And those tangent lines intersect each other. And those are really the breakpoints of the piecewise linear function. So I call those tau i's. But my variables of interest are the linearization points. It's better to do it that way so that I guarantee that I have a convex underestimator of my original function. So a little picture, here are the tangent lines at these linearization points, and where they intersect are these p's, giving me my piecewise linearization. So if you will, it's just the convex envelope of these tangent lines. Just a little notation. So I call P0 the linearization point at the left, and Pn plus 1 the linearization point at the right. All of this I said already. Yeah, and what follows, you're going to see a function g, and g always means this piecewise linear function. So if I give you a function f and I say take it to g, I mean the piecewise linearization. It depends, of course, on the function f, but also on the linearization points I chose. So the g always depends on the function and those linearization points. That's the vector of linearization points. So that's what g means. So the first thing, and sorry about all this notation, but I better start unpacking it now. L and U, you know what they are. That's the range for the x. G is that g I talked about. We're given an f and we produce this g. But of course, to do that, I need these points. And don't worry about that little cap over things. That has to do with some latent notation that's not important. And star just means perspectivization. So what is this object? It's take a function f, do the piecewise linearization in the way I described, now perspectivize it in the way I described, and look at that three-dimensional set in the XYZ space. What's its volume? So here's what the volume is. It's exactly this. So what are those taus? Well, those were the points in the X space where those tangent lines crossed. And I need to compute the g function at those taus. The g is the piecewise linear function. And that's what it is. It's a very simple linear time algorithm to get the volume. This AD, that is absolute determinant, but actually things are arranged very carefully, so you don't even need the absolute value if you care about that. The things are oriented the right way so that all these things are actually positive. So the point is that this is not a hard object to calculate. What I do is I forget about z. I look in the z=1 plane and calculate the area of this object by triangulating it. And then the perspective is really nice with volumes. It's just a pyramid with height 1 over that base. And so once you realize that, you just realize that you just have to compute the area of that base in the z=1 plane, and then the rest is just some, silly constants. So that object is easy to get the volume of. It's not quite a closed form expression, but it's a very simple expression. So what can you do with that? Well, you can start to analyze things, and most of our detailed analyses are for particular functions like power functions. Well, for a quadratic function, that's always the nice place to start with convex power functions. What you can prove is that if you fix n, the number of breakpoints, the volume of this set, remember I do the piecewise linearization, and then I perspectivize, the volume of that set is minimized with equally spaced breakpoints. And this is what the minimum volume is. If you let n go to infinity with equally spaced breakpoints, you're getting the actual function itself. And so you can immediately recover that the volume of this of the set without doing the piecewise linearization is exactly that. There's also the naive relaxation, and in this first paper I mentioned, the Jogo paper, we calculate that. So the naive relaxation for the quadratic function, the volume is exactly that. And what you can see then is if you pick even one well-spaced breakpoint and then perspectivize, that's stronger than doing the naive relaxation. So you don't need a lot of breakpoints to beat the naive relaxation. Even one well-placed one and then perspectivizing it. Now that's weaker than just perspectivizing the original function without doing the piecewise linearization, but perspectivizing that function gets you into conic programming. And if you do one breakpoint and linearize, you don't get forced into conic programming, and you can still do rather well. So that's the point of this. It's helpful to get some understanding about how the optimal breakpoints vary for different p. I just said when p is 2, we have equally spaced breakpoints. What this picture is here's the interval. I just did an example from L = 0 to U = 1. So there's 0 and 1. And if you look at the power 2, you see here are the optimal breakpoints. They're equally spaced. When the power of a power function is bigger than 2, then the points get clumped up to the right. So this is giving you some guidance of where you should put your breakpoints if you have a function that's growing faster than a quadratic, or curving faster than a quadratic. On the other hand, if you go between 1 and 2 for the power, things clump up the other way. So we can prove this in general, not just this one picture, but generally speaking, the optimal ith breakpoint, when you fix the number of breakpoints, is increasing in the power. So it's just here summarizing a few other results that we have. First of all, just some observations. Getting a closed form expression for even one breakpoint for power functions that are not quadratic seems to be out of reach. So if you just want a closed form expression for where should I put one linearization point between L and U, and it's not a quadratic function, that seems to be out of reach in terms of closed form expressions. The function, the volume function, is not even generally convex in the location of that one linearization point. So that's part of the reason why you can't expect a closed form expression. But what we can show is that any stationary point of the volume function, so the variables now are these linearization points, and this is an arbitrary dimension, any stationary point is a strict local minimizer and more. Actually, when the power is between 1 and 2, the volume function is actually convex. So I said it's not generally convex, but it is convex when the power is less than 2. And so in that case, if that's your exponent, then any nonlinear programming algorithm that will find a stationary point will find a global minimizer of the volume. So you can actually calculate the best place to put the breakpoints in that case just by using IPOpt or something like that. For the case p greater than 2 is actually quite interesting. We were able to simplify the condition that the gradient equals 0 and establish that the volume function also has a unique stationary point. And another neat thing is that if you try to minimize this function over the breakpoint and do Newton's algorithm, so not just in one variable, but in all the breakpoints, it's monotone. So, we saw this behavior of the where the breakpoints move when p is bigger than 1 or bigger than 2 or less than 2. But actually, if you start at equally spaced breakpoints and then you start doing Newton's algorithm, so in this case the points are decreasing, but it's also for increasing. The points monotonically move to where they really should be optimized. So what it means is that if you're using, say, Newton's algorithm, and it's slowing down, you still know, well, if I do another few iterations, it will improve, maybe not by a lot, but it will always improve step by step when you do Newton's algorithm in terms of getting closer to the optimal breakpoints. So we look quite a bit at where do I put the optimal breakpoint. I said we don't have a closed form expression, but we'd still like to know should we put an optimal breakpoint for arbitrary power functions, even just one breakpoint. And that's useful even in the multiple breakpoint case, because what I could do is look at the odd numbered breakpoints and realize that moving around a single breakpoint between its adjacent even ones is just the one breakpoint problem. And these are all kind of separate. So I can iteratively go back and forth in parallel between the odd numbered and the even numbered breakpoints and do something quite fast in a sort of coordinate descent style. So that's why it's interesting to think about algorithms and bounds on where a single linearization point should be placed. So expanding on what I was saying before, this volume function for a single breakpoint is strictly convex, actually, in that breakpoint. But if the power is bigger than 2, it's only quasi-convex. So the lower level sets are convex sets.
John, sorry to interrupt. So we are 2 minutes away from the 25 minutes mark.
Yes, we are. Thank you. Let's see. So because of this convexity or quasi-convexity, it doesn't matter. In either case, we always get that this volume function has a unique minimizer there. So for the case where it's not convex and only quasi-convex, a very simple function, it's just some constant minus the volume, is actually strictly log concave. So minimizing that gives you the global minimum. So in both cases, p bigger than 2 or less than 2, it's quite easy algorithmically to get the global minimum volume and find out what the optimal location for a single breakpoint is. We got quite interested, though, in trying to localize these breakpoints as well as we could. We already know in the quadratic case, the optimal point is the midpoint. But what about in the non-quadratic cases? Can we just say something rather than have to proceed algorithmically? So what we did is we got bounds. If p is in that range, then that single breakpoint should be between these two values, actually always to the left of the midpoint, which is what we saw in that picture with the 5 curves. Maybe it was 4 curves. And then things flip around. If p is bigger than 2, it's a similar thing, and you're to the left of the midpoint. So, I mean, these are complicated expressions, these guys here. It's the same thing there. So these two things are complicated expressions, and it would be nice to understand, are these good bounds or not? Are they close to each other or not? So it's hard to deal with that because you have the L and the U, and so you have 2 degrees of freedom. So we parameterize this in a certain way. We let T be L over U, so a number between 0 and 1. And then we define delta P of T. So this is, I haven't defined this notation, but it was just those 2 things I circled on the previous slide, that upper bound and lower bound. And we want to know, how does that upper bound and lower bound, the difference, compare to the size of the interval that we're looking at? So with this parameterization, you can rewrite this like that, just in terms of P and T. And so now we can start to play with T and try to understand how this behaves. The first thing is that we could show that this delta PT can be bounded in a useful way by delta P0. P0 is L equals 0, right? Because T is L over U. So the thing is, if we can completely analyze the case of L equals 0, lower bound equals 0, it turns out that will tell us quite a bit about how this behaves in general. And that's because of this result here, that delta PT is worst case delta P0 as an upper bound. We would like the similar thing on the lower bound side, but it's not really true. You have to put a correction factor there of this 1 minus L over U. But still, it gives us some idea about knowing something about delta P0. What does it tell us about delta PT? So delta P0, we drop the 0, and it's just this. So that's just plugging in T equal 0 here. And this is what the function looks like. So this is delta of P, that kind of error factor, and as a function of P. And so we can see that's P equal 2, no error at all. So these bounds really tell you that the midpoint is optimal when P equals 2. And otherwise they vary, but they don't get too bad. So the worst case is as the power goes to 1, that factor becomes 1 over E. And then there's this mysterious value at a power of 6.32 right here, but also it's not so bad. So generally, this delta P is between these constants. And so what it's saying is those bounds localize the true minimum quite well. There's a whole nother chapter here, but I'm going to stop. There are other relaxations. You'll have to look in the paper to see what's going on with them. And we have some results about where to, how many linearization points you should use, where to put them, that kind of thing. So I'll stop there. If you want to read more, look at the archive version there. That would be your best source. Both of these conference versions have considerably less than are in the journal version, so you really want to look at the journal versions. Oh, and yeah, I did say I would say something about this. With Lusa, we're looking at the multivariate situation where X is not on an interval, but it's in first a simplex and then more complicated low dimensional polytopes to try to get some similar results. So have a look. I think, I gave you a flavor of the results. I didn't give you much of a flavor of the proofs, and you'll see if you look at these papers, some of the stuff is, maybe it could be made simpler, but the way it was very complicated for us. So you'll see that there's a lot of analysis got involved. I do want to mention one thing before I stop. Dan gave a talk yesterday with 0 integer variables. My talk has 1 integer variable. So things are moving in the right direction.
Okay, thanks, John. So there are a bunch of questions in the Q&A. Maybe I'll take just one. I'll repeat just one, and then the other one can be taken. Can we move to Slack? So I'll take the one by Jeff. In some cases, minimizing the volume of the object is the same as minimizing the maximum difference between its top and bottom, when it is not true? And can the problem of minimizing the maximum difference be easier?
So by the difference, you mean the value of the function, Jeff? Is that what you mean? Jeff, I can't answer. Yeah, I like it when Jeff can't talk, actually. This is really a big benefit. But yeah, so if you have a lot of symmetry, and you can see this in the paper with Walter Morris back from '94, if you have a lot of symmetry, there's not too much, and you're in low dimension, there's not too much difference in looking at the difference of the the value of the function versus these volumes. But there's no general result like that. And yeah, it's a different problem. And generally, I think it's a harder problem at least in higher dimensions, because you can't take as much advantage of symmetry. Volume is a hard thing to compute. So it's computationally hard. And the way you can get away with closed form and algorithms is some special structure. And that means either a low dimension where you can brute force things, which in a sense is what we did, or symmetry, where you can sort of really use low dimensional arguments because you have symmetry, or sparsity, where you're looking at like volumes of polytopes that come from graphs, and that graph has a low tree width or something like that. You need some lever like that. So low dimension, sparsity, or symmetry to get a handle on volumes. And so if you're looking at different kinds of objects or different things to compute, whether it really is volumes or mixed volumes or any kind of integrals, really, you need some kind of lever to get away from the fact that these things are Sharpie complete in the worst case.